In this tutorial, I'll be covering the notations, basically the output, how to read the output results of SAP 2000 or ETAPS, the CSI package, and the notations, and the myths between modeling shell, plate, and membrane elements. So if you go to these three elements, right? So I'll be going to a summary only. So if you consider a membrane, so membrane does not have out of plane stiffness. It only consists of in plane stiffness, meaning that it cannot take bending, right? In plane forces only. So I'll give you one example. And for plates, right? So for plate element, these will have some thickness, right? Even membranes as well, right? For plates, you will have only out of plane stiffness, right? Not in plane. It cannot take in plane in plane forces, but it can take out of plane bending. So the perfect example is a reinforced concrete slab. Yeah, if this is the side view, so we know that if a load is applied, slab does not, the concrete does not take by these membrane invent forces, right? There's no such there's no such force membrane forces develop in the slab, right? When your load is applied. In contrast, what it does is there will be stresses like this, top compression, bottom tension, and thus it will have bending, right? So it will have bending forwards. So it takes out of plane bending. But no in plane forces, right? No in plane forces. So if you calculate the in plane forces in finite element software, so you will get 0, right? And for shell element, this is basically a combination of both membrane and plate, right? So in plane and out of plane. So it can resist in plane forces as well as the outward out of plane forces, right? So basically, uh, it can actually, so this is just an arrow, okay, not the force or moment, okay? So out of plane uh, about this axis, let's say it bent like this, or else about this axis it can bend like this, right? So that plates can take that bending, but membranes cannot. Shell element can take both. Right? So I'll be showing you an example in the, yeah, let's first I'll show you the membrane. The perfect example is a balloon, piece of balloon, right? So we'll go with that. Perfect example is, as you can see, so this is a membrane, right? Example for a membrane, a piece of balloon. So you can see you stretch axially, right? You provide the force in the plane of the balloon piece, right? That is the in plane, right? Plane, in plane forces. So you stretch in the plane, right? so it can resist the in-plane forces, right? So stresses will develop, right? Once the stress is larger, so that will break, right? Until that you can press. But what happens if you uh, provide out of plane loading? Let's see what happens if you just uh, rocket, right? You can see it cannot take bending, right? Whatever the out of plane load applied, so it just deformed, right? It does not have any flexural rigidity, right? It cannot resist bending. But if you consider a slab, it is not like that, right? It has some stiffness and take bending, right? Ability to resist bending, right? So this piece of membrane does not have a flexural out of, in other terms, out of plane stiffness, right? So here we saw the in plane stiffness. It can resist these in plane forces, but it cannot resist the out of plane forces, right? So hope you got the idea. In the membrane, we only have this kind of, in the plates, you only have, so since I don't have perfect example to show you, the perfect example is slab. So there we do not have any membrane forces developed that cannot take membrane forces, but uh, it can take actually slab piece plate, because we don't usually see in plane loading, right? Don't see, and because we only have out of plane loading, right? So idealization for a plate is okay, right? For a shell element, it has both in plane and out of plane stiffness, right? So next we go to the SAP outputs. So usually outputs can, so if you provide the local axis, right? Global XYZ is the global coordinate system. For each element, that SAP will define a local coordinate system, right? So that the red axis will tell you the first axis, green axis the second one, the third axis is the blue axis, right? SAP won't show the numbering, but how to keep this in remember: red is 1, green is 2, blue is 3, right? So if you consider a shell element, right, doesn't matter whether it is membrane, plate, or shell, right? So, and one more thing, there's something called uh, thin shells and thick shells, right? So what you mean by thick is when the thickness increases, you will have uh, transverse shear influences, right? So that means that you have to account for that as well. So for a good example is like something like a pile cap, right? That will be modeled as thick shell, right? And if you consider this shell element, you can see axis is 1, and there will be 2 faces, right, perpendicular to that axis, and always the positive face is where the axis is directed. Axis positive direction, right? And which face meets that, that will be the positive, and this will automatically become the negative, right? This will automatically become the negative face, right? So axis 2, as you can see, this is the positive face, right? This is the negative face, and axis 3 positive face is this one, negative face is this one at the back, right? So if you go to force internal forces, right, always keep in remember these shell internal forces, doesn't matter again membrane plate or shell, it's showing the tab called shell stresses, right? So within that you can have these everything, and depending on which section you initially idealize, whether this is a shell, membrane or plate, that will give you the results, right? But the default tab is shell results, right? Shell stresses or shell forces. And you can see these forces are calculated given at the mid surface, right? Keep this in remember. Mid surface stresses are, this is the mid surface, right? Okay, so and the possible actual distribution of F11 will be like this along the height, right? But SAP calculates only the shell elements, the internal force values at shell element joints only, right? These values only, then it interpolates the behavior, right? SAP assumes the distribution of F11 along the shell mid-surface graphically, right? This is for plotting purpose only. Next, we'll discuss what is this F11 and other things, right? So F11, so this is axis 1, this is axis 2, this is axis 3 coming out of the plane, right? So F11 always means the stress along the direction, sorry, the force, right? So these all forces are forces per unit length, okay, at the mid surface, right? And calculated at the corner points, right? So F11 is the force per unit length along the first direction, right? So you need to know what is the element uh, local direction, right? These are according to the local element coordinate system, right? Local axis, so, right? So F22 means the force along the second direction per unit length, right? You can see, okay, and you can see F12 is acting on, this is coming from this first plane, okay, first on this first plane along first direction, right? This is on second plane, right, on second direction. But F21, which is F12, right? So is shear component, right? So that will be acting on, so these are equal, okay, F12 and F21. So this is acting on the second phase, but on along the first direction, and as well as this is acting on first positive phase along the second direction, right? So these are done, these are done. These are called the membrane forces, right? Okay, major, right, along 1 and 2, right? Okay, so this will also be there, right? And for V13, right, V13 is along the uh, along the first positive surface, but in the direction of third axis, right? It's coming out of the presentation slide, right? Coming out of the presentation slide, and as well as this is going inside, going towards the presentation slide. That's the direction of this force, right? I hope you understand. And similarly, it is V23 is, that's the shear on the second phase, right? Second phase, whether the positive or negative, and the direction will be given by the next subscript 3, right? V2 3, right? Okay, so keep these two in remember, okay? And if you go to F max and F min, so you know that you have studied the mechanics of material. So if 2D state, right, you rotate the element such that you need to find the principal stresses, right? So such concept is applicable to this, and you can find the principal forces. So if you this is the original element, you rotate some amount, right? So such that you find the maximum and minimum forces, right? Principal forces that we see, right? Okay, and there will be some other angle, right, where you need to rotate, and you will find the maximum shear, right? Pmax along this face, right? Transverse shear, maximum transverse shear, right? Okay, Vmax. Okay, so and Vmax can be calculated at any angle, right? Any angle you take V1, V12 and V23, V13 and V23, and plug into this equation, right? That will give you Vmax. Okay, so this will give you the principal forces at such rotation of the element, right? There will be in you will get the maximum force and minimum force, right? So F max is the principal force, right? Principal major one, F min is the principal minor, right? And can go to internal forces still and M11. Here it's little bit tricky, and these all moments are per unit length also, right? And acting still the mid surface. Okay, and this is valid as well, moments at the element corner points. And this M11 is it's not like the beam bending, right? M1 means, you can see this is M11, the direction is given by, right? So this double arrow means you need to use your right hand finger, and it's like Maxwell's law, right? This is the direction, right? Rotates. So M11 is this bending moment. M22 is moment above this line, right? It's M1 means not the moment above first direction, right? It's like the moment about second direction, M1. M22 is moment about first axis, right? Little bit tricky, not like in the beam, right? Okay, so let's say if you have a slab, right? Let's say your first axis is this, second axis is this. So if the slab bends like this, right? So that means you have moments like this. So this bends about one axis, so that means this is M22, right? So if it bends like this, it bends about 2 to second axis, so that means this is M1 M11, right? So this is the twisty moment, but it's really hard to interpret this one using simply, right? So this is twisty moment, and yes, for a slab you need to know these things, right? Shell element, which moment to take, right? M11 or M22, right? It depends on the local axis. And for similarly, you can take a max and a min principal moments, right? Maximum moment and minimum moment, right? So this will be the angle where you need to rotate to take the principal moments, right? Okay. And for internal stresses, there you have something several called S11, S12, S13, S22, likewise, right? So these elements, right? So unlike in the forces output, so stresses are calculated at both surfaces, top and bottom. Forces only at the mid surface, right? Stresses are top and bottom surface because if you have something like this, you have tension, compression here, tension here, right? Right. So those are calculated at still at the corner points, but at the both surfaces, right? So this will give you the membrane direct stress, right? So that means stress at first phase along the first axis, right? First direction. That will give you the membrane direct stress, right? So it's on the first phase, and as well as the direction is axis 1, right? And this is the membrane direct stress S22 on the second phase, on the second direction, right? So other things are shear stresses similarly. So this will give you the phase first subscript. It's on the first surface, but on the second direction in this way, right? S12 stress, and it is equal to S21, right? And similarly, this will give you S13. The surface is first one, right? First positive surface, which is 3 is the direction, right? And likewise, this is S23. The surface is 2. The direction is third axis, right? So out of the plane, right? Out of the presentation, let me say, right? So possible distribution of S11 is like that. Don't confuse with J1 middle node and J2, right? Because the SAP, even the internal stresses, top and bottom corners, right? Corners only, right? A, B, C, D only, not they calculate SAP calculate at A, B, C, D on right corners, but stresses are calculated at top and both surface, bottom surface, both. Forces only the mid surface, where you can get the stress at J force at J1 and J2, right? So that's the difference, right? So this will be the stresses calculated from SAP, right? So that will interpolate the other things and give you the distribution if you need the plots, right? So we'll go to SAP, and similarly, you will have such rotation such that you get the maximum principal stresses and minimum principal stresses, right? And minimum principal stresses. So shell element stresses are reported at corner points, like I told you, and these transverse shear stresses calculated S11 and S22 are average values, right? It's like average shear distribution, but you know that it's not like that. Shear stress distribution is something parabolic, right? So even for rectangular element, it is 0 at the ends. At the middle, it's maximum, right? So we can use the same approach approximately. Maximum or minimum transverse shear is 1.5 times average shear stress, right? So this maximum, if you need to maximum transfer shear stress, you can calculate by this, uh, like we calculated in the shear force, right? And yes, X max, and this is shear, right? X minimum. All the things are there. So this is the rotation of the element such that you get the principal stresses, right? Not on the axis of, not on the, not along the local axis directions, right? So these are the outputs along the local coordinates, right? This is the principal stresses. This is the maximum transverse shear stresses, right? So I will use the same box culvert and some wall where it is loaded at the middle. I will show you the loading. If you want to see the loading of yeah, I will show you load assigns area. I will show you the, it's like a shear wall. I have loaded that like this, right? So along the y direction, I have applied a uniform pressure, right? Y direction is this, right? I have applied stress for only these elements, right? I have supported pin supports for these, right? And I have provided some point loads as well. Joints. So you can see I have applied point loads at here, and I'll show you the local axis as well for areas. And you can see this is the first direction, this is the second direction. So we are applying this force at along the second direction, right? So the major membrane stress should be, membrane force would be F22, right? F11 is in the longitudinal direction and out of plane direction is 33, right? So you can see this right side will be the negative phase. If you consider this side is the positive phase for third, right? Because this is the positive side, so this is the positive phase of the element, right? Top, right? So this is the bottom phase, right? Top and bottom, right? So for this shell box culvert, I'll show you the loading. If you want, you can check my previous video on box culvert. I have clearly shown you. So for the area, I'll show you the HB loading. So that's like this, right? I have loaded it in these elements, but that load is intensity is high, right? 75 kilonewtons per meter squared acting on Z direction, downward direction, right? So the local axis you can see I have marked, right? So it is bending like this, right? And like this as well. It is majorly bending like this and like this as well, right? Along this direction, right? And so that bending moment is given by, this is 1, right? This is M11. This is 2. This is 2. this is M22. Okay, keep those things. Remember, I'll analyze that, run all the cases. Yes, I'm not sure which section I have used, which sections I have used for the top slab. I'll be using slab of 600 for this top surface. Okay, so that is membrane, right? So I'll use shell thin. Okay, right. And for this as well, for now, shell thin. Okay, right. So the load case I need is copper shells. I'll use for HP loading. So that's for due to the vehicle live loading. So results and forces. You can see F11, F22, these are membranes, right? F max, F min, these were the principal forces, right? F, this is von Mises stress, right? You combine those things and give you the uh, von Mises stress, right? So these are M11, M22, M12, the moments, right? And these were the principal moments, right? So shear components, this is, as I remember, transverse shear maximum, right? And now you know what are these, right? So if you consider, if you need F11, let's say this, right? So you can see, according to our loading, membrane stresses is very low, right? It's around one something, right? But according to the out, because we analyze this to outer out of plane loading, right? Not in plane loading. In plane loading, I have applied for second one, right? Second goal. I have separate the model. So there should be M11. Let's see. You can see M11 is first direction is like this. First direction is this, right? So that M11 is this bending, right? And M22 is, see, due to this sagging, right? So you can see the values, right? If you want, now you know the stresses as well, right? So you go, so these are the forces, right? So let's say the maximum, if you want, you can show it from the, so these are the principal stresses, right? Principal forces, right? So these are the principal. So you, if you consider rotating the element such that uh, it will give you something like this, right? So that it will show the, can you see, angle is shown from the direction one, right? Maximum and the minimum stresses, right? Those are the principal stresses. Okay, so maximum transverse shear, right? So just separate some element and think, draw it like this as I shown you in the PowerPoint slide, and try to interpret these results, right? First time or second time, that is not easy, but with time you will manage, right? So go for shear stresses. That will show you visible phase. So that means the phase we can see, and top, bottom. So top is the positive phase, bottom is the negative phase, as I shown you in the presentation. And the maximum is whatever the maximum of those top or bottom, right? So let's see the the membrane stresses, okay? Membrane stresses, and we'll go with S1, okay? Stresses. So you can see this is 300, around 365 something, right? So that is maximum, right? Then let's see the minimum, right? Minus 356, right? So we'll go with the top surface. So top is the underside. You can see the side of this sign of this blue arrow, right? Top top is top surface is this one, right? Okay, this surface, right? So and that was the top, and the bottom is this, right? You can see the visible face is the bottom, right? 356. If you get the bottom face, that will also give the same result, right? Visible surface, right? Because the top is at now actually bottom, because you can see the local axis 3 is towards the downside, right? So maximum, I think maximum is yeah, maximum is in the top face, right? So if you click maximum, nothing will change, right? Can see. So likewise, you can play around with this, right? If you want, you can see the absolute maximum as well, right? So I told you what are these things. So these are the principal stresses. I think I shown you already. So one measure stress that combines everything and give you the stress, right? So there's an equation where one measure stress. I haven't uh, uh, I haven't inserted in this PowerPoint presentation. I will if I can, I will try to give you that equation as well. So that combines everything on measure stress, and then the maximum shear stress, right? So these are the membrane stresses as I shown you earlier, right? So I will go to the force outputs of this wall, right? So here's a bit tricky, right? So this was also a shell element, right? This is also shell element, and you go to shell resultant forces. So we have membrane forces and out of plane bending. Let's check membrane force F1. It doesn't, sorry, this is not HB loading. We have to go with SW loading. So you can see some stress values are shown, right? So this is first direction, right? But we applied vertical point load in axial this second direction, right? In the green arrow shown by, right? So let's check those values, F22. So there should be some likewise, right? Can you see? So the point where we apply the, so you can see the increase in stresses, right? Stress increasing to the point where we apply this, right? Load. It's like a contour, right? It calculated the nodes and these forces at the mid surface, right? And this is for the in-plane point loads, right? Let's say for the out of plane moments. So you can see this is the bending, right? M11. So that means it's like this, right? see M11 and M2 to M. So M11 is bending moment like this, right? Okay. M22 is bending moment like this, right? Moments about second axis, right? So that will give you something like this. So you can see, right? You can see it clearly. So, and this is now a shell, right? So resultant forces. But what happens if you provide a membrane? So we go to model. So this is also a slab of 450. So we modify it as a membrane, right? Okay. Then we analyze it. So for you can see, so you have still the membrane forces, right? F11. Oh, you can see, and if you consider, so you have the membrane forces, right? Sorry, yes, membrane forces you have in this window as well. But if you have moments, right? If you check the moments, let's say moments, so you can see it's zero, right? Why? Because this is a membrane and it does not have the ability to resist when the moment. In other terms, it does not have out of plane stiffness, right? And if you consider the plate, it's the other behavior. So we'll modify the section as a thin plate, right? And we'll analyze. So for a plate, you have the bending moments. It have the ability to resist out of plane bending, but you can't have, it does not resist in plane forces, right? It can't take, right? So it's zero. No membrane forces, right? No membrane forces, but it has out of plane bending, right? But so for a membrane, you had only membrane forces, not out of plane moments are zero. And for a plate, your bending values are there, but membrane forces are zero. In a shell, both are there, right? Membrane forces and uh, the uh, out of plane moments are there, right? So there's some myth, right? So if you consider some slab, so reinforced concrete frame for the slab, you can use actually the slab behavior is plate, but still, so people use shell thin, that's okay, right? But people use membrane as well. Why? Is it wrong? No, because if you want to define the frame elements, right? What happens if you uh, model the slabs as membrane? So membrane will not absorb any bending moment. So that moment will be absorbed by the beams and the columns, right? So that means rather than a plate, right? These, if you provided a membrane for the slab, so all the bending will be absorbed by beams and columns, right? So it's quite conservative, right? So you are designing for a larger value. So that is conservative. That's okay, right? If you provide a plate or shell, so your plate and shell have out of plane stiffness, so that it will take bending as well. So that the moment taken by the beams will be lesser than compared to the membrane, right? So that will be more realistic. But if you want, you can take membranes and for the slab and model and take the bending moments from the frame elements, right? So I hope you understood the concepts and the local axes and everything, and how to read the outputs for the shell stresses and shell forces, right? One misses and principal stresses, principal moments, and stresses, the phases. What are these phases? Visible phase, top phase, bottom phase. So top phase is the positive phase, bottom is the negative phase. So thank you very much.